Okay, let's have a look at number 3. First task in this one will be simply to read the problem and pull out the information that we need. So we have two groups here, type A and type B, and we have a sample size, a sample mean, and a sample standard deviation given for each of those. The sample sizes were 100. The sample means are 4.1 and 4.4. The sample standard deviations were 3.1 and 3.8. I'm squaring those now to get 0.0961 and 0.1444. Neither of those is twice the other. 0.1444 is not greater than twice 0.0961. Therefore, we can pool. When you pool, the degrees of freedom is equal to NA plus NB minus 2. 100 plus 100 minus 2 is equal to 198. And then when we pool, the standard error is equal to the big formula. S squared A NA minus 1 plus S squared B NB minus 1. All that's over NA plus NB minus 2. And then take all of that, 1 divided by NA, and multiply by the square root of 1 over NA plus 1 over NB. So in this problem, that'll be the square root of 0.0961 times 99 plus 0.1444 times 99. All of that divided by 198. And then take all of that and divide it by 1 over 100 plus 1 over 100. And you should get 0.049. So that'll be our standard error. We'll want to keep track of that. So remember that we pool, that our degrees of freedom is 198, and that our standard error is 0.049. Of course, I'm going to be erasing this and writing some more. You should have it on your paper, so if you don't remember, you can always look back on your paper. The other thing we'll do is we'll go ahead and find the critical value for the t. This is the critical value for the t. It's also the confidence coefficient for the t. And so we're going to go to the t table, and what you're going to do, let me come over here. We've got a lower than, so it's going to be a one-tailed test. And so you're going to go one-tailed test, 0, 5, and down to 198 degrees of freedom. And what you're going to realize then is the table only goes down, I think it's 100 degrees of freedom. So if you'll just go down every column there, you'll see that the larger and larger your sample size is, the t starts to get closer and closer to the value you would have with the z distribution. So close, in fact, that it's practical, or certainly for our purposes when we're using the table and everything, to simply use the same value as the z value. So with this degrees of freedom in a one-tailed test, we use 1.645. This is the critical value when we do the t test, and it's also the confidence coefficient when we come down and construct the confidence interval down here. So for the research and null hypotheses, it says is the population mean for A less than the design for B, or the population mean for B. HO is always going to be mu A equal to mu B. Alternatively stated, mu A minus mu B is equal to 0. So getting to part C, we're going to reject HO if t-test is less than minus. So if we had a less than here, this is less than minus. We're rejecting when we get into the lower tail, and of course those are minus values when we get down there. And we had that as 1.645. And so the t-test is equal to the statistic minus the hypothesized parameter which always that part is going to turn out to be 0, at least in this class and most applications, divided by the standard error. That wouldn't be 0 if we said, is mu A less than at least 10, or at least 10 less than mu B, but that's seldom used, and we won't use it in this class. We'll have that be 0 all of the time. So anyway, this comes out to be 4.1 minus 4.4 minus 0 divided by the standard error of 0.049, which is equal to minus 0.3 divided by 0.049, which is equal to minus 6.12. Think about this for a minute. This means that we're 6 standard errors below the mean. You know, if we were drawing this out, and we will in a minute, that means we're down here. Just remember, plus or minus 3 would have about all of the data, so we're quite a bit further even than that. That is less than minus 1.645. So now we will reject HO, and we will conclude that mu A is less than mu B. We can use that to decide which design to use. I assume we want a lower residue, so we ought to use design A. That new design has yielded an improvement that's worth making changes for. Okay, you'll need to use your calculator to obtain the p-value. So just do stat, 2-sample t-test, plug in the numbers. You will say pool, or yes when you get down to the pool, and you'll say less than when you get to the choice between less than, greater than, and not equal to. So here's a picture. I'm not sure why that's doing that. Did it last time too. But apparently it's only doing it once. I can live with that. I'm drawing like this because I know that value that we observed, the minus 0.3, is way lower than our hypothesized difference of 0. And in fact, when you computed that p-value, you should have had 2.5 times 10 to the minus, what was it, 9th. If you wanted to write that out, you would have 8 zeros. And that's a pretty low number. It's close to 0. Part D, Part E, we'll reject HO. If p-value is less than 0.05, 2.5, I'm going to put e to the minus 9, just with an exponent of minus 9. Or you can write this number however you want to write it. It's small. It's less than 0.05, so we reject HO. And we conclude mu A is less than mu B. Of course, the same conclusion we already had using the critical value approach. And then for part 2 on that, we will say if mu A minus mu B is equal to 0. Of course, you could have put if mu A is not equal to mu B. Then there is a very small, minuscule 2.5 times 10 to the minus 9, a very small chance of obtaining x bar A minus x bar B. Keep putting parentheses just to reinforce the idea that this is one number less than minus 0.3. Again, it's so small that you would reject HO, reject the idea that it came from a sampling distribution or a population where the difference between two sample means was 0. So for the confidence interval, we'll take the statistic plus or minus a confidence coefficient times the standard error. The statistic was minus 0.3 plus or minus 1.645. Goes with 90% times the standard error of 0.049. When I calculated that earlier, I got minus 0.38 to minus 0.22. And that is an interval that does not include 0. In fact, all the values are less than 0. So we can conclude mu A is less than mu B. Or at least we can say that we're confident that that mu A is less than mu B.